Hey everyone, so today we are talking about ICE tables, which stands for Initial, Change, and Equilibrium. In our past lesson, I gave you all the equilibrium concentrations, and you were able to plug that into your equilibrium expression and solve for K. Well now, I'm not going to give you all the equilibrium concentrations. I'm going to be just giving you some initial concentrations, maybe one equilibrium concentration here and there, and you're going to have to figure out a way to solve for K or solve for your equilibrium concentrations. And that's where our ICE tables come into play. So stay tuned. We're going to go over how to set up these ICE tables and then eventually solve for our K and other equilibrium concentrations. Alright everybody, so we're just going to dive into a problem here where we're going to have to use the ICE table. So let's read this problem. I have an initial concentration of 1 molar CH4 and 2 molar O2. At equilibrium, CO2 has a concentration of 0.5 molarity. Calculate K. And some of you guys might be thinking, oh, okay, I just plugged this into my equilibrium expressions. I got 3 concentrations, I could plug that into my KEQ, and then I could solve. But here's the problem. You can only plug those in when you have equilibrium concentrations. And unfortunately, we have 2 initial concentrations of 1 molar and 2 molar, and only 1 equilibrium concentration of 0.5 molar CO2. So you gotta start looking at your questions and seeing what actual concentrations they give you. If they gave you 3 equilibrium concentrations of CH4O2 and CO2, then yeah, just plug it in to your equilibrium expression and then you could solve for K. But here that is not the case. We were given some initial concentrations and we are giving only 1 equilibrium concentration of CO2. So this is where you gotta say to yourself, okay, I gotta use an ICE table. So what is an ICE table? Well, what we usually do is we set up our equation and then we'll write ICE down the side, okay? And then we're gonna fill in an initial for each reactant and product, a change for each reactant and product, and an equilibrium for each reactant and product, okay? But first of all, what we can do is we can get rid of any compound that won't affect our equilibrium. And if we remember correctly, the only things that affect equilibrium are gaseous state atoms or compounds and aqueous state compounds. So we know that water is not going to affect our equilibrium at all because it's in a liquid state. So we are just going to ignore that all together. Okay? I, initial. That stands for our initial concentration. So we're going to go ahead and we're going to look at our problem and we're going to see if they gave us initial concentrations of anything. Hey, they did. It says, I have an initial concentration of 1 molar CH4. So I'm going to put a 1 here. They also gave us an initial concentration of 2 molar O2. And then CO2, they didn't give us anything, right? And that's probably because it's a product, right? We probably just put these concentrations together and we didn't even have any CO2 initially. So what we can do is we can put a 0. And if they don't ask you to solve for initial concentration or they don't give it to you at all, you could just assume it's 0, okay? Especially if it's a product. Change. Change is the tricky part that some people get caught up on, but it's really simple, but you just got to pay attention to what I'm saying here. Change is what you expect to happen in the reaction based on the coefficients, okay? The reactants, we expect them to lose some of their concentration, right? When the reaction happens, they're going to lose some of it, maybe a lot, maybe a little. Since they're going to lose, we are going to put a negative for each reactant in the change area. And then our products, we expect them to gain something. So we expect their gain to be positive. So we're going to put a plus sign on the product side. That's for every single one. Reactants will always have a minus sign. CO2 will always have a positive sign. Well, what are they going to change by? We don't know. So we're going to put an expression x, okay, or 2x or 3x. And depending on if it's 1x, 2x, or 3x is based on what coefficient is in front of each compound. So since CH4 has a coefficient of 1 in front of it, we're just going to say that it's minus x. Since O2 has a coefficient of 2 in front of it, we're going to say it is minus 2x. And then since CO2 has a coefficient of 1 in front of it, we're just going to say it's plus x. So get that through your brains, okay? Whenever we do change, it's always negative on the reactant side, positive on the product side, and then we're going to put either x, 2x, 3x, or 4x there, and that's going to depend on the coefficient in front of our reactants and products. So we did 1x here, 2x here, 1x here, because it matched up with the coefficients. And then equilibrium is just the equilibrium concentration. Okay, sometimes they give us an equilibrium concentration, and we could just plug it in there. Sometimes they don't. So if they don't give us an equilibrium concentration, what do we put in there? We just combine our initial and change expressions, right? So for this one, we don't have an equilibrium concentration for CH4, so we just combine I and C and make our equilibrium expression 1 minus x. We don't have an equilibrium concentration for O2, so it's just 2 minus 2x. And we could do the same for CO2. 0 plus x is going to just equal x. But here's the thing. They gave us an equilibrium concentration for CO2. And thank goodness, because you'll see later on that's going to help us solve this problem. So CO2, they gave us an equilibrium concentration, so I could just put in 0.5 for my concentration there. And now I would say to you, okay, it's time to plug this into our equilibrium expression. But here's the thing. Do we know what x is? We should, right? Because remember that initial plus concentration equals equilibrium, right? 1 plus minus x equals 1 minus x. 2 plus minus 2x equals 2 minus 2x. 0 plus x equals 0.5. So what must x equal? It must equal 0.5, right? That's the only way this could have gotten to 0.5. So then that means now that I know that x equals 0.5, I could solve for these guys. I could figure out their equilibrium concentrations now. I now know that this guy's equilibrium concentration is now 0.5. I know that this guy's equilibrium concentration is now 1. And of course, we know that this guy's equilibrium concentration is now 0.5. I'm not done yet, right? I still got to solve for K. So that means I got to go ahead and make an equilibrium expression now. So this is a multi-stepped problem, as you can see. So I'm going to erase this stuff on the top, keep this equation so that we have room for our K expression. So it says calculate K. Remember, our K expression is products over reactants, forgetting anything that's a liquid or solid. So products over reactants, it's just CO2. Reactants, I have concentration of CH4 at equilibrium, and O2. Am I forgetting something? Yep, I'm forgetting the exponent of 2 right there for my O2. It's redundant, but the coefficient comes into play in your change column, and it comes into play in your equilibrium expression as well. So now we just got to solve for K by plugging and chugging, right? We already have equilibrium concentrations thanks to our ICE table, so now we can just plug away. CO2 is 0.5. CH4 is 0.5. And 1 is 1 squared. So I plug this into my calculator. 0.5 divided by 0.5 gives me a K of 1. And you might say to yourself, K equals 1, what does that mean? Does that mean I have more products? Does that mean I have more reactants? That means that my reaction is at equilibrium. It's at the end, okay? So that means that it's no longer changing, it is equalizing. That means we're going to have similar amount of products. The reaction is done shifting left to right. It is at equilibrium. That's what that means. Okay? So that is an example of where we use our ICE table. There might be situations where I don't give you nice numbers and you gotta figure out or do a mathematical expression to solve it on your own. Let's do a little bit of a tougher one now. All right, everybody, here's one that's going to get a little tricky on us. So assuming the reaction contains only reactants initially, what is the equilibrium concentration of CO in an equilibrium mixture of 0.5 molar H2O at 1,000 degrees Celsius? So here, it gives you a reaction. It actually gives you the K, which is nice. And it wants the equilibrium concentration of CO. I'm looking here, I'm seeing, okay, it doesn't really give me much, but the equilibrium concentration of 0.5 molar H2O. Let's just do an ice table to see if this can help us in some way. So let's go ahead and do that. So I'm going to set up an ice table. And I know right off the bat, since this is solid carbon, I could just go ahead and forget that one because he's not going to affect it at all. So let's go ahead and let's see what we could change here, or plug in here. Initially, it says, assuming the reaction contains only reactants initially. So we know that it only contains reactants initially, so we could put a 0 for these guys. Unfortunately, it doesn't really give us anything for H2O. So let's just go ahead and put a question mark right there because we are not really sure if we could put anything there right now. Let's go ahead and put our change, right? We know that the reactant side will be negative and the product side will be positive. They all have a coefficient of 1, right? So this is just going to be negative x, this will be positive x, and this will be positive x. And then I'm going to go ahead and plug in any equilibrium concentrations I have. Well, it says the equilibrium concentration of CO in an equilibrium mixture of 0.5 molar H2O. The only thing it really gives us is that 0.5 molar H2O at equilibrium. Okay, it doesn't give us anything for CO and H2. So now, let's just combine what we can, right? We know initial plus concentration will equal equilibrium. So these two, 0 plus x, are just going to be written as expression x. And I can't really figure out my change in x, unfortunately, right? They didn't give me an initial concentration. I can't assume it's 1. I can't assume it's 2. I just don't know. So I'm going to have to go at this a different way. I have something, though, for each equilibrium. So that's good. So why don't we just go ahead and make an equilibrium expression, plug in what we know, and maybe we could solve for x. All right, let's do that. So I'm going to erase this top part. That 100 degrees Celsius, they'll do that all the time. It doesn't really mean anything. It just means that in the future you'll see that changes in temperature can change our equilibrium expression. But anyway, let's go ahead and write our equilibrium expression, plug in what we know, and maybe that'll help us solve for x. So equilibrium expression is products over reactants, which is concentration of CO and H2 over concentration of H2O. And let's plug in everything we know. This is new. We actually have K. So let's just plug that in, 0.2. Okay. We don't know CO and H2, but we do know they're both X. And we do know H2O's equilibrium concentration, which is 0.5. All right. This is starting to look like something we could solve. This is starting to look algebraically like something where we could solve for x. So let's go ahead and try doing that, okay? Let's go ahead and combine like terms. Well, first of all, let's get all these numbers to one side. I could times 0.5 to both sides, and I'll get 0.1 equals x times x is x squared. Hey, looky here, I can go ahead and I could square root both sides, and I can actually solve for x. So I'm going to take the square root of 0.1, and I'm going to get x equals 0.316. All right, so you're going to be doing that. If there's a point where you get stuck and you don't know what to do, just plug it into your equilibrium expression and see if you can solve for something, okay? Well, x equaled 0.316. Well, don't forget you got to plug it back in to this last expression. People forget to do that all the time. This, it's fine, right? Because x, it's just x. I don't have to change anything. But what if this was 2x? Well, then I would have to multiply my x by 2 to get my equilibrium concentration. But thankfully, my equilibrium concentration was just x, so my concentration of CO at equilibrium is just 0.316. 0.316. And then if I wanted to, I could actually figure out the initial concentration of this, right? Because now we know the change in x is 0.316. So then I just add x to this to figure out the original concentration of 0.816. I'm not asking for that though. Okay, just a cool thing that once you find x, you can figure out all your initial concentrations, all your changes, and all your equilibrium concentrations. Okay, so that is another example. Now let's do one where if we get stuck algebraically at this point, a little trick we can do to help us solve the problem. Okay, so here is another example of ice tables. So I'm looking at this and it says at 35 degrees Celsius, K equals 1.6 times 10 to the negative fifth. You initially have 0.5 molar NaCl. What are the concentrations of all species at equilibrium? So I'm looking at this and it wants to know all the species at equilibrium. It gives me a K, it gives me initial concentration. I'm probably going to have to do an ice table here. Now, I want you to look at this K. And notice that that is a whole lot less than 1. So if that means there's a whole lot less than 1, that means that this isn't going to produce a whole lot of products, right? It's really reactant favored. So this reaction isn't really going to shift right very much. That will come in handy here in just a little bit. But first, let's set up our ice table. So initial concentrations, it gave us 0.5 molar NaCl at the beginning, and then we could just assume that our products are 0 if they don't give it to us, because this reaction hasn't happened yet, so there's not going to be any products. Let's go ahead and do our change. Remember that reactants are negative, products are positive, and then we just got to put x based on the coefficient. There's a 2 here, so this will be 2x. There's a 2 here, so this will be 2x. And there's just a 1 here, so this will be x. And now let's go ahead and let's plug some stuff in. Do we have any equilibrium concentrations? No, we don't. Darn. So let's just go ahead and combine our I and C and see what they give us. So I plus C is going to be 0.5 minus 2x. 0 plus 2x is just 2x. And 0 plus x is just x. Alright, we're kind of stuck here. So let's go ahead and let's just plug this into our equilibrium expression and see if we could go anywhere from there. I am going to go ahead and write K down here because we're going to need that in a little bit. So let's go ahead and let's erase this and now start our equilibrium expression. Alright, let me write my equilibrium expression first without any values. K is products over reactants. I got NL to the squared because there's a 2 in front. Cl2 over reactants, which is NaCl to the squared. Okay, now let's plug in our values and see if we can get anywhere from this. So I know my K to be 1.6 times 10 to the negative fifth. I know NO is 2x, so 2x to the squared. I know Cl2 to be x, and I know 0.5 minus 2x to the squared. And now you might be thinking, oh boy, simplifying this is going to be really, really tricky. I know that 2x becomes 4x squared, and then I could combine it with x to become 4x cubed, but then this becomes really, really tough, right? I'm going to have to use FOIL to multiply these together, and it's going to end up giving me something to the second with a 2x or a 4x in the middle and a 0.25. That's going to be a huge mess. So I'll show you a trick to make this a lot easier. Okay, So whenever you get a K that is really, really, really small like this, 1.6 times 10 to the negative fifth, that means there's not going to be a whole lot of products being formed. That means that there's not going to be a whole lot of change in concentration of this guy, right? If that K is really small, that means that this reaction isn't going to progress forward a whole bunch. So what we can do, if you ever have a K, or you get in a situation like this, frankly, but if you ever have a K that is really small, I'm talking negative fifth onward, so negative fifth, negative sixth, negative seventh, negative eighth, you could just assume that the change is going to be so small that it's pretty much going to be zero, okay? But just on the reactant side, okay? We still got to figure out some sort of concentration here. So we're just going to assume that since K is so small, the amount of change from that reactant is going to be minuscule. So we could just make this just 0.5. It's almost going to be the same. So now that I've gone ahead and just assumed that that change is 0 and I'm only left with 0.5, I could just get rid of that in my expression as well. And that makes the math a whole lot easier. All right? So just to recap, if the K is really small, negative 5 onward, negative 5, negative 6, negative 7, we can assume that that change is going to be so small in the reactants that it's pretty much going to stay the same. Okay? So, again, only if the K is really small. Just assume that the change in the reactants only is going to be 0. So I'm just leaving it at 0.5. That makes us solving it a whole lot easier. So let's go ahead and erase this, and let's go ahead and solve this, or simplify this a little bit more. So now it's 1.6 times 10 to the negative fifth, 2x squared, 2x times 2x. A lot of what you guys do as a mistake is you do these. And you just say, oh, it's 2x squared. No, remember, this was in square brackets. So it's 2x times 2x. So that's going to be 4x squared, and then times x once again. 0.5 squared, I know it, I just have no faith in my mental math, so it's 0.025. Alright, let's go ahead and get everything on one side. I could do 0.25 on both sides. I could combine these terms as well. So I should get 4 times 10 to the negative sixth. And then this should become 4x to the third. Alright, divide by 4. So 4 second e to the negative 6 divided by 4, I know this one as well, I don't know why I'm doing this, is 1 times 10 to the negative 6 equals x to the third. And then we just cube root this, or you could just take it to the 1/3 on both sides. And you should get an x that equals 0.01. Alright, so we did a lot of math. We kind of did a little shortcut there. We cheated a little bit and assumed x was 0. We did some algebraic expression here and ended up getting x equaling 0.01. Well, let's remember what our ice table looked like. So I'm going to go ahead and I'm going to go rewrite that here. Alright, so I have rewritten my ice table right here, and now I'm included my expression back in here because I want to figure out what the concentrations are at equilibrium. So now I'm going to plug in 0.01 for my x for all of these. So now I'm going to plug in 0.01 here, 0.01 here, and 0.01 here. So I already have Cl2. This just becomes 0.02 as my concentration for NO, and then this becomes, because I don't trust myself, 2 times 0.01, 0.48 as my concentration. That makes a whole lot of sense, right? Remember, our K was super, super small. It was that 1.6 times 10 to the negative fifth, right? So you should assume that you're not going to create a whole lot of reactants here. So that is a situation in which you can assume x is 0 because that k was so small. Let's go ahead and let's do a couple more examples and then we'll be done. Okay, so another example. At 30 degrees Celsius, we have 4 molar of SO3 is put into a container and it begins to dissociate or decompose. At equilibrium, 1 mole of SO2 is present. Calculate K. So let's go ahead and do that. We need to calculate K, but we need all the equilibrium concentrations to do that. They didn't give us all the equilibrium concentrations, so I'm thinking ice table. So I'm going to put ICE down here. All right, and let's go ahead and plug in what we know. Do I have an initial concentration for SO3? Yes, it said it was 4 molar. They didn't give us any concentrations for SO2 because it hasn't dissociated yet, so we can assume that these are 0. Let's go ahead and find the change, right? Again, reactant side is negative, product side is positive. Since there's a 2 here, it's going to be 2x. 2 here, it's going to be 2x. And 1 here, so it's just going to be x. And then we find if we have any equilibrium concentrations. At equilibrium, we have 1 mole of SO2, so we just have a 1 here. All right, well, at least we got 1 equilibrium concentration. Let's combine the rest. We got 4 minus 2x, I plus c. 0 plus 2x is going to equal 1. That'll come into play later, as you could probably guess. And 0 plus x is just x. Well, you might ask yourself, okay, let's plug this into our k expression. Well, that's not going to help us because we don't have k. We need to have k in order to solve for x by plugging it into an equilibrium expression. But, luckily, we can use 0 plus 2x equaling 1 to solve for x, right? Initial plus change has to equal equilibrium. So that means that 0 plus 2x must equal 1. So what must x equal? X must equal 0.5, right? If x equaled 0.5, that would equate to 0 plus 2x equaling 1. So now we could just go ahead and we could plug in x to these final expressions to get our new equilibrium concentrations. So the equilibrium concentration is just going to be x, which is 0.5. And then if we plug in 0.5 here, our new equilibrium concentration for E is going to be 3. Cool, we got all our equilibrium concentrations. But we're not done yet, right? They want us to calculate K. Well, in order to get K, we better go ahead and write an equilibrium expression. Always do this with just the reactants. Don't just try to plug away or else you'll forget an exponent, I guarantee it. Alright? Like Men's Warehouse over here. So, let's put our products over reactants. SO2, I gotta square it because there's a 2 in front of it. And then I got my reactants, SO3, and I gotta put a 2 there because it is a 2 in front of it. And now let's go ahead and plug in what we know. I don't know K, but I know my O2 concentration is 0.5. I know my SO2 concentration is 1. And I know my SO3 equilibrium concentration is 3. I'm going to go ahead and plug this into my calculator here. 0.5 divided by 9 essentially. Just double checking, yeah. And you should get a K that is equal to 0.056 no units. 0.056. That makes sense too, right? Because we had a whole bunch of SO3 to start, and we didn't really get a whole lot of SO2 or O2, and our K represents that. It shows that we're going to have more reactants than products at the end. All right, one more example, and then we're done. All right, last one. Calculate all equilibrium pressures with an initial H2S pressure of 0.824 atm. And you might be thinking pressures, and then you might remember, oh yeah, right, we can use concentration or pressure for this equilibrium chapter. So here I just switched it up and threw a pressure at you. So I'm looking at this, they want me to calculate all equilibrium pressures. they don't give me anything but initial concentration and a Kp over here, so I better be using an ice table. So equilibrium, let's figure out what we got. We just got 0.824 ATM, and then we can assume those other guys are 0 because they are products. We're assuming nothing was there at the beginning. Change, negative for our reactants, positive for our products. I'm going to make sure all these are gases or aqueous. They are good, so I can include all of them. This is going to be negative 2x. This is going to be 2x. This is going to be x based on the coefficients. And then they didn't give us any equilibrium concentrations because they're jerks, so we're just going to combine I and C to get our E. So I'm going to have 0.824 minus 2x, 2x, and x. 0 plus 2x is x, 0 plus x is x, 0.824 plus 2x minus 2x is 0.824 minus 2x. Now I'm kind of stuck. They haven't given me anything, but luckily they gave me a Kp. So let's go ahead and just do an equilibrium expression and see where we can go from there. So I will go ahead and do Kp equals products over reactants. We got H2 gas squared because of the 2. We got S2, and we got H2S squared because of the 2. Let's plug in what we know. I know Kp is 2.2 times 10 to the negative 6. I know H2 is 2x, so we'll do 2x in parentheses or square brackets and square it later. Let me fix that. I'm going to put x in square brackets and incorporate that later. And then I'm going to have 0.824 minus 2x squared. And now you might be thinking, this looks ugly. I don't want to do this math, this algebra. Let's see if I can neglect the change on our reactant side. So I'm going to look at my Kp and I see that, wow, that is really, really small. There's not going to be a whole lot of change on the reactant side. The change in concentration isn't going to be a whole lot because that Kp is so small. So I'm just going to assume that is going to be 0. So I'm just going to get rid of this minus 2x all together. And that makes my job a whole lot more easier. Okay, I'm going to go ahead and I'm going to continue this down here. All right, because I don't want to erase my ice table just yet. So let's go ahead and continue this down here. We got 2.2 times 10 to the negative 6. I know 2x squared, 2x times 2x is going to be 4x squared, times x later on, which will just be 4x to the cube, but we'll do that later. And then 0.824 squared, let's just go ahead and do that. 0.824 to the squared is 0.679. Let's go ahead and multiply on both sides, right? Times 0.679 times 0.679. And I'll have a little bit of room over there, so let's go 0.679 times 2.2 second e to the negative 6th. I will get 1.49 times 10 to the negative 6 equals 4x squared times x is 4x to the third. Divide by 4 on both sides. I get, I'm going to move this up here now. I get 3.73 times 10 to the negative 7th equals x to the third. And then I just cube root both sides, right? I go to the 1/3 to the 1 divided by 3, and I will get x equals 0.0072. And you might say, okay, equilibrium concentration done. Not really. Okay, we got to go ahead and we got to plug this in to our equilibrium expressions and figure out our new concentrations. Well, the new concentration of S squared is just going to be X, which is 0.0072. Oh, sorry, not concentration, right? We're not doing that anymore. We're doing pressure. Okay, 0.0072. Remember, this is now x 0.0072. So my new equilibrium pressure is now, I can do this in my head, 0.0144 atm. That's my new equilibrium pressure. And now here, remember this used to be minus 2x. So let's go ahead and plug in 0.0072. And now I'm going to have to use my calculator for this one. 0.824 minus 2 times 0.0072. And I should get, I'll put it over here, 0.8096 ATM. And that matches kind of what this was all saying. Kp was really small, so the initial concentration should change a whole little, and the equilibrium pressures should be very little as well. So that is ice tables. Make sure that you are figuring out how to set them up, figuring out what steps you need to take, when you can neglect that X when that Kp or Kc is so small, and make sure, most importantly, that if you get stuck, you're asking questions. That's it. Have yourselves a great day.